Hello, everyone. My name is Hunter Cedillo, and this is going to be Group 1's ME425 design project, and we're going to be discussing the Mascule Bridge project. To outline the presentation, we're going to go over some introduction, goal and requirements, concept, go over some of the CAD, its dimensions, and then bills of materials. And then finally, we'll go over our justification using analysis, the statistical analysis, shaft, gear, and fatigue. So the goal of the project is to design a movable bridge that will have safe passage for not only passengers over the bridge, but also passengers using the waterway under the bridge. And here we have our requirements. It's going to, again, hold time requirements, dimension requirements, and safety requirements. And we can move on.
So hi, I'm Scott Colmar. I conducted the static analysis for the bridge. So as Addison mentioned, he conducted the brainstorming phase of the project, or we all did, that is. And that was more to move into the later phases of the design, including the gear analysis and the power output that was needed to move the bridge. The point of the static analysis was to better refine the bridge itself to cut down on the amount of weight needed, as well as cut down on the material necessary for it. And so this was to give us a better idea of what kind of safety factors we need to apply while designing the bridge, as well as what standards of safety need to be incorporated in terms of those set by like ASME, by NMDOT or other similar organizations. Moving into that, the analysis itself was conducted as looking at the bridge as a simple beam structure with hinge to hinge supports with a distributed load. The distributed load itself would be a combination of the vehicles on the bridge as well as the bridge's weight itself due to the concrete and steel components. And with that analysis, we're actually able to move into a script, which I'll actually discuss here in a second. That script itself was based on the fact that this bridge has a bit of an odd construction, given that it's made of multiple components. When you use different materials, you would need to find a way to relate themselves to one another to do the stress analysis. And to do that, use the transferred section method. And this method basically uses the Young's modulus of the two materials used to come up with a ratio. And you apply that ratio to the moment of area of one of the two objects so that you're able to get it in terms of the other. So basically, I was able to use this method to come up with a moment of area for both the steel and concrete components. Using that second moment of area, I was then able to calculate the stress given the internal moment based off the weights applied, and then a simple Y factor based off the cross-sectional area. And then, of course, in this next slide, I believe I actually have an example of the script itself. So you can see there at the bottom is the actual outputs and inputs. So those first 8 or 10 lines or so, this is where an operator would come in and input the Young's modulus of the steel being used, given that concrete is a variable in some manner, given a lot of environmental factors, a lot of laying factors. So a more known constant is usually that steel factor of whatever you're using. And in our context, we were using the ASTM A992 steel, which is pretty common for this concept. And with this script, we were also able to input the different dimensions of the flanges and beams used on the actual structure itself. And so what that was able to do is we were actually able to calculate the safety factor reliably and repeatedly with different components on board. And so going back to what Hunter talked about at the very beginning on using just components off the shelf, we're actually able to go in and just find catalog components and input the parameters of those into the script and basically get the safety factors and weights accounted for that we needed. So that basically takes care of my section. I'm going to hand things over now to Addison, I believe.
Hi, so I'm back with some information. I will continue on the selection of certain parts of our bridge, including the counterweights, the shaft, and the bearings. Starting off with the counterweight selection, there are two main options when it comes to counterweights for Mascule bridges that are very common in industry. The two options are lead and tungsten. You can see pictures of them on the side. The top one is lead, but it has a painted coating for protection against weathering and for handling protection. Here are the pros and cons. Lead. The pros of lead are that it's cheap, dense, it can come from recycled materials, it's easy to work with and easy to maintain or replace. The cons are that it's less dense than tungsten and it can be harmful. The pros of tungsten are that it's more dense than lead and it takes up less space. The cons are that it's 10 times more expensive, it's hard to machine and work with, and it's not easy to maintain or replace. So with our final choice, we chose lead. Recycled lead could be a great counterweight while reducing lead release into the environment from sources such as recycled batteries, etc. And here you can see there are some lead weights on this Bastille Bridge. It's a pretty good example. And now I'll move into the shaft material. The materials we were choosing between were steel and tungsten, where steel is cheap and readily available. The bridge is made out of the same material, so everything would wear at the same time. It's very easy to work with, easy to replace, and easy to repair. A slightly larger shaft is needed, but cost savings are huge. And for tungsten, it's expensive and hard to work with. It's super strong and dense, which would allow for less material, and it would provide less deflection for the same shaft size. But the pros for tungsten did not outweigh the cons, and so our final choice was steel due to the cost and manufacturing benefits. Now getting into the shaft diameter. The final shaft diameter was chosen based on the Tower Bridge and some beam analysis. Here you can see the Tower Bridge in London, and you can see some general measurements that have been made. And based on these measurements, we kind of estimated a shaft diameter of about 4 feet for our shaft. And then using the second area moment of the shaft, we were able to, and the Young's modulus, we were able to calculate the deflection at different points. And originally with 2 supports, 1 on each end, deflection was larger than we were happy with. So we chose to add more supports in order to reduce the deflection, ending up with a max deflection of 0.62 millimeters. Then on to the bearings. Bearings are needed because without the bearings, the shaft would have to rotate on the supports. And since the shaft is carrying such a large load, the friction would make turning the bridge impossible. So we were able to find some bearings that actually have a 4-foot bore, which would support our 4-foot diameter of the shaft. And here you can see the ratings for the bores. This bearing here is specifically made by SKF. It's a custom bearing, and that is the route we would have to take in order to get a bearing that we needed. And here are the C10 calculations based on the forces, the application factor of 1.2, and assuming all the other things, we got a C10 of about 4.6 and the C10 of about 9.3, and this is in kilonewtons. And now if we go back to this table right here, everything is in pound force. So after you do the conversion to kilonewtons, we are well beyond we are well beyond the C10 that we needed. Now moving on to Daniel's section. Oh, to Xavier's section, right?
Thank you, Addison. My name is Xavier Graham, and I'll be going over the bill of materials. For our bill of materials, our main 2 items that cost the most are the reinforced concrete and the lead for our 2 counterweights. And we can see that those are approximately $3 million and $8.5 million. And then our 2 main standard components that we can buy off the shelf are 2 different I-beams in 2 different lengths of 75 and 25 meters. And then we have our bearings, which will need to be custom made, as Addison mentioned. And then we have our 2 shafts, and then our 2 gear sets that will also need to be custom made out of grade 1 steel. And then we have our motors And then in total, this all costed around $12 million. And now onto Hunter's section.
Thank you, Xavier. So finally, we get to our first model of our design here. And there's a couple things I'd like to point out. I'd like to start with the two fixed end conditions spanning the 200 meters of the bridge. That's either going to be leading into either side of the land. So we can either consider that to be the land fixed end or our own supports. And then the innermost supports are going to be actually the pivot points for our dynamic portion of the bridge. And those are actually also going to be hollow housing our motors and gears as well. And then we also decided to do a support in between the innermost supports and the outermost supports to minimize any deflection in the static portion. And then on the right side, we have a kind of a zoomed in portion of the CAD model, so we can really start to see how our concept is coming together. On the top layer, we have our reinforced concrete, and then the bottom layer, we have our I-beams. And then the black portion, which you can see here and here, is going to be the lead cased counterweight. And then we have our dynamic portion leading out to the center. And it's actually interesting, if you look right under the shaft section, we introduced this support system here. And this was to mitigate stress concentrations in that orientation when the bridge is in operation. So then I'll pass it on to Daniel.
Thanks, Hunter. Hi, everyone. My name is Daniel Romero, and I'll be going over our basic gear design and analysis today. So we began by depicting a basic diagram of the machine elements that are used in our design. Next, it was important to label the interactions between the moving parts. Some of the important factors here were the torque and the angular velocities to begin with. And then we needed to determine information about the bridge and how it would move. So we modeled its movement off of an actual bridge, in this case, the London Bridge, which has an operating angle of 90 degrees. And it does that in about a time of 75 seconds. So using these values, we can determine the rotational velocity that we're looking for. And so with the torque and angular velocities determined, we could use relations between the gears, assuming a certain amount of gear teeth, to transfer that torque and angular velocity to the shaft being driven by the motor. The torque was determined by using the rotational mass moment of the bridge itself, including products of the angular velocity and also the angle of rotation. So with the torques and angular velocities determined, we were able to decide on a rough idea of the gears and then used an iterative process to determine their dimensions. Next slide, please. And this brings us to the design of the gears themselves. So we begin this by modeling the two-dimensional pitch circles. And the pitch circles are important because they allow for proper meshing and functioning of the gears. To do this, we look at the diagram of the gears and then break them into two separate objects and using free body diagrams. And this allows us to view the relationships between the torques, the forces, and the radii of the gears. And by estimating a radius, this allows us to determine the transmitted load on the gear teeth. And this transmitted load is necessary to determine the stress on the teeth. And this brings us to our next slide, which is about the design of the gear teeth themselves. So an important consideration here was to determine the material that the gear would be made out of. And through research, I determined that typically gears components in a bridge are made of grade 1 steel. And this was important because it allowed us to determine information about the yield strength of the material. And that is further important for determining factors of safety. So with our transmitted load already determined, which you can see represented by W with the superscript T on the diagram on the slide, with that value already determined, we could focus on the tooth dimensions themselves. And we know this because when you observe the equation for stress, it involves the transmitted load and geometric properties of the tooth. So when focusing on the tooth geometry, it was important to keep the length small and the footprint of the tooth large, because this effectively reduces the stress experienced by the gear teeth themselves. And the stress was determined, and that would be 40.8 megapascals. And with an allowable stress and a factor of safety determined, we could estimate a factor of safety of 13.5. And onto some fatigue considerations. When it comes to gears, the fatigue is generally involved by the rotation of the gear and the contact stresses that it incurs. And when something incurs a large amount of contact stress, subsurface, there is a lot of shear experienced, and this can result in material chunks actually being emitted from the gear itself, and this is called pitting. So to reduce the chances of pitting from contact stresses, we went ahead and decided that we could do a hardening process on the gear to a particular Brinell hardness factor. And to end, I'd like to mention that this gear analysis was really focused on the pinion gear. And this was important because the pinion gear is the smaller of the two gears in our operation. And when you have a larger gear, you have a larger area, you have more teeth. So it would essentially be undergoing less stress. So the smaller gear was the important one to consider for the design here. And this leads us to our next section.
Thank you, Daniel. So now that we've talked about the analysis and the justification for the gears, we can actually implement them into our model. So on the left, we have the true model, and this is going to have our shaft that was calculated, and then the two gears that Daniel just discussed. And we can see how those fit into our model. Again, those are nestled into the supports, and this is going to be in each of the four supports that we have attached to the dynamic portion of the actual bridge. And then on the right side, we can see that we have a reduced ordered model showing the motion of the bridge and how those the pinion gear is going to interact with the main gear to the shaft, and then finally to the bridge. And then we can go to the next slide. To supplement our analysis, we went through a computational analysis using finite element. We did a static analysis. So we took the bridge and we fixed it at each support on the bottom there. And then we also modeled the shaft portion as a fixed condition. Based off of our numerical analysis we did, we can assume that that portion is also going to be roughly a fixed condition. So then we applied the maximum load calculated again through that worst case scenario. We ran it through a converged mesh and generated a max stress and a max displacement and the locations of those. So on the bottom left here, we can see where the maximum displacement would occur, and it's where you would expect in the center of the bridge. However, that maximum displacement is minimal, rounding out to around 2.5 millimeters, and that's something we're okay with and meets our safety requirements. We also generate a max stress, which is around 70 million newtons per meter squared. And that's actually going to occur where the supports are right under the shaft. And that's how you know the shafts are the supports are working, because they're taking a lot of that maximum stress. If we go to the next slide, in our iterative design process, we would also go through a frequency analysis, where we would run through essentially the same setup, but we would run through and generate natural frequencies and mode shapes. We would then compare those to excitation frequencies that our bridge might see, earthquakes, hurricanes, and ensure that our natural frequencies are not lining up with any of those excitation frequencies to avoid the resonance phenomenon, which can cause damage and essentially catastrophic failure to our bridge. And then the next slide is going to be our conclusion, and that's going to round out this presentation. We've justified that our bridge meets the requirements, the dimensional requirements, as well as the safety requirements, and we use numerical and computational analysis for the justification of that. Thank you.